Hello. In this video we're going to take a look at some properties of Hermitian matrices, that is, matrices M, which are equal to their Hermitian conjugates, which by definition means they are equal to their complex conjugate transposed, which is equal to the transposed complex conjugate. Okay, so let's take a look at some results. First, theorem 1. Hermitian matrices have real eigenvalues. Let's show that in the worked example area. Okay, so to prove theorem 1, we can take our matrix and its corresponding eigenvectors, defined as follows. And we can act the Hermitian conjugate on both sides. So bearing in mind that, remember, if you have two matrices A and B, and we transpose those matrices, then we get B transpose A transpose. It's not too difficult to prove, and you can do it in the problems. And so similarly, if we have A, B Hermitian conjugate, we get B Hermitian conjugate, A Hermitian conjugate. So acting Hermitian conjugate on both sides of this, remembering that a vector is just an n by 1 matrix, so its Hermitian conjugate is a 1 by n matrix, we just get VI Hermitian conjugate, M dagger, and over here we have VI Hermitian conjugate, lambda I star. Okay, so this already tells us that you can kind of naturally think of the matrix as acting to the right on vectors and the Hermitian conjugate of the matrix acting to the left. Since we're only going to be considering Hermitian matrices, it tends not to play out as much of an issue, but it can be useful to bear in mind. Okay, so it's convenient then to consider the following construction. So consider this. Let's take VI M dagger minus M VI. Okay, so this object must equal, well, we know that M acting on VI is just lambda I VI. So we can turn this M into a lambda I. And M dagger to the right of a VI, like this, should equal lambda I star VI. Okay, so all we've used is the top two relations. But if this is true, well, this thing in here is a scalar, right? It's just one potentially complex number minus another. So we can pull it out to the front, and we have lambda I star minus lambda I VI VI. But we assume that our eigenvectors are normalised. We're always going to normalise them. And so this thing just equals 1. And so the thing on the left equals lambda I star minus lambda I, but if our matrix is Hermitian, then by definition, M dagger equals M. Okay, so this thing in here is just 0, so we have 0 on the left-hand side, and so we have 0 equals lambda I star minus lambda I, which means that lambda I star equals lambda I, and the eigenvalues of a Hermitian matrix are all real. Okay, let's head back over to the board. Theorem 2. The eigenvectors of non-degenerate Hermitian matrices are orthogonal. Non-degenerate here means that no two eigenvalues are the same. Let's take a look at it in our worked example area. Okay, this time let's consider this object instead. We're going to consider VI acting on M dagger minus M Vj. Okay, so just as before, M acting on Vj is going to, by definition, equal lambda J Vj. M dagger acting on Vi, as we saw in the previous example, is it was lambda I star Vi, like this. This was a star, but we've already proven that the eigenvalues of Hermitian matrices are always real, so we can just omit the star here. So this thing equals lambda I minus lambda j, Vi, Vj in a product. Again, this thing on the left is equal to 0 because m dagger equals m. So we have 0 equals this. So we see that provided that lambda I never equals lambda j, we have that Vi, Vj equals 0. So the eigenvectors of a Hermitian matrix are orthogonal, provided that the matrix is non-degenerate. No two of the energy eigenvalues, of the eigenvalues are the same. That's what we wanted to prove. Theorem 3. The normalised eigenvectors of non-degenerate Hermitian matrices form complete orthonormal bases. The proof from this actually follows from the first two. If you must have n eigenvectors for an n by n matrix. If those vectors are orthogonal, which theorem 2 tells us, and we normalise them, well, if they're orthogonal and there's n of them, they must span an n-dimensional space. So it must form a complete basis. And we've normalised them, so they must in fact form a complete orthonormal basis. Theorem 4. Defining the eigenvectors to be Vi and the eigenvalues to be lambda I, we have that the identity, the n by n identity matrix, can always be written as the sum from I equals 1 to n of the outer products of the normalised eigenvectors. In fact, we showed this in the previous video. We proved it for a general complete orthonormal basis, and theorem 3 tells us that the normalised eigenvectors of non-degenerate Hermitian matrices form complete orthonormal bases. And finally, theorem 5, we can write the Hermitian matrix M as the sum from I equals 1 to n of the eigenvalue lambda I multiplied by the outer product of the corresponding eigenvector Vi with itself. In fact, theorem 5 follows straightforwardly from theorem 4. Given that we have the identity matrix equals this, we simply act with the matrix M onto here. M acting on the identity is M. M can pass through the sum here and act on its own eigenvector, and M acting on Vi, by definition, is lambda I Vi. And so this identity follows straightforwardly. Let's take a look at this for a particular example on the next board. There's an example of a Hermitian operator, where an operator is a slight generalization of a matrix, which we're very familiar with at this point in the course, and that is the Hamiltonian. So the Hamiltonian we're familiar with from this equation, the time-independent Schrödinger equation, where we see it acting on its eigenfunctions in giving the eigenvalues. So you can see there's a close analogy between vectors and what's going on here. In fact, as we'll see in a later video, functions of x, say, or anything else such as this, are really actually infinite dimensional vectors. So we've already done the difficult case earlier on without realizing it. If we consider instead finite dimensional Hilbert spaces, so remember a Hilbert space is a complex linear vector space with an inner product and normalizable states. In a finite dimensional Hilbert space, rather than an infinite dimensional one, which we've been effectively working with when dealing with functions, we can just write the following, where our function has been rewritten as a ket or a vector because we're now dealing with some capital N dimensional Hilbert space, which is finite. In fact, it's very common in quantum mechanics to rewrite this state. The phi isn't really serving a purpose here, as you can see, and we can just rewrite this as follows. So rather than call it phi subscript n inside the ket, we can just call it n inside the ket. N is just a label, so rather than calling this a vector like v, for example, we can just call the vector n, bearing in mind that the only thing we're ever going to really require of it is that it return our eigenvalues e subscript n. Okay, so it's a convention, but a widely used one. If we write it like this, then by the argument on the previous board, theorem 5, we can rewrite our Hamiltonian in the following form. That is, it's the product of its energy eigenvalue En with the outer product of the corresponding normalized energy eigenvector n, or phi n if we use the older notation. And you can check straightforwardly that this matrix H obeys all the properties you'd like it to obey. For example, it returns the right eigenvalue. That is, we can act this whole object onto M, and the M is happy going in and out of the sum. But this object here, by definition, remember that we have a complete orthonormal basis for our eigenvectors of any Hermitian matrix, but in particular of the Hamiltonian. This thing is just a Kronecker delta, defined to be 1 when n equals m and 0 otherwise. So it selects from the sum the case that, oh sorry, I've written this sum over I. There should have been a sum over n in this case. It selects from the sum the case n equals m, and so we just get the result E subscript m acting on m. But that's precisely our time-independent Schrödinger equation. So that works. And we can also check that this matrix is by definition Hermitian. The Hermitian conjugate of H, we complex conjugate the energy, but the energies are real, so this is equal to En, nothing changes. And the Hermitian conjugate of the matrix formed by n outer product n, remember this is a big N by a big N matrix, well, clearly it's just you flip them round, but you just get n outer product n again, so you get exactly the same thing. So this thing by construction is always Hermitian. And we find that H dagger equals H, and so H is Hermitian. Okay, so there's a simple example of putting some of these theorems to use. All right, thank you for your time.